Hi class, welcome to the fifth lecture on electrodynamics. And our main reference here is again Introduction to Electrodynamics by David J. Griffiths. And as I've always told you, I hope you can buy one of the books. And this is recommended for you. This will help you in understanding the lectures. So we have studied about line integrals and surface integrals. Now we move on to volume integrals. In the volume integrals, you have an expression of the form. Here you have an integral of a function t, which could be multivariable, and you'll be integrating that with respect to an infinitesimal volume element d tau, and d tau is just a product of in this case you have a Cartesian coordinate system. D tau is just a product of dx, dy, and dz. So if you have a vector function, then what you do is to split the vector function into its components before you can integrate with the volume integral. So here you have the vector function and then its three components here, then doing some algebraic distribution, then you will have this one, and this one here. For here you have your direction x outside of the integral, because x and of course y hat and z hat, x hat I mean, they are independent of the space. They're independent of x, y, and z. So your x hat is a constant vector, your y hat is a constant vector, and your z hat is also a constant vector, unlike in the spherical polar coordinates and in the cylindrical coordinate system, that your variables there, most of the unit vectors there are space dependent. So for Cartesian unit vectors, you can take them out of the integral because they are constant unit vectors. As an example, you have here, calculate the volume integral of t equals x, y, z square over the prism in figure 1.24. So you have here a prism that has, in this case you have the x is dependent on the value of the x, and the y are related to each other. In this case you have a linear relation between x and y, but for x and z you have independence of x and z, and you don't have any relation for y and z as well, because as you can see here, it's the same triangle as you can see here. So it does not, the triangle did not change, so only x and y are related to each other. So if we get the linear relation between x and y, you have here, you have this is 1, 0, xy, no? And here you have 0, 1. So you can get the equation of the line, which is the relationship between x and y. So this is like you have 2 points, 1 and 0, and then you have 0 and 1. So you can have x minus 1 over y minus 0 is equal to 1 minus 0 over 0 minus 1. So you have x minus 1 equals times negative 1 equals y. Or you have x equals 1 minus y. So that's the relationship there. So if you integrate that, you go to the next page. So you have three integrals here, dx with respect to dx, with respect to dy, and with respect to dz. So you can, by the way, as you recall, t is equal to x, y, z square. So you have your z square here, y, and then you have x. You can integrate either first, you can integrate z first, or you can integrate y first, or you can integrate x first. But when you integrate x, you have to immediately integrate y, because they are related to each other. So you have here the limit 0 to 1 minus y, because of the relationship between x and y. So the integral of x dx has the limit 0 to 1 minus y. It's not 0 to 1 because the value of x is dependent on y. So you have here the integral of x dx is equal to x squared over 2. So the 1 over 2 you can write here, and then x squared minus 0 squared. This is the x is 1 minus y squared, minus 0 squared will just be 1 minus y squared. And then you have the y here and the y here, and then you integrate with dy. So in this case you have here 1/2, and then the integral of this is z cubed over 3 from 0 to 3. And then you have the integral of this is this can be written as y minus y cubed. So you can integrate that as y squared over 2 minus y to the 4th over 4 from 0, evaluated from 0 to 1. And you can show it by yourself that this is equal to 3 over 8. So we proceed with the fundamental theorem of calculus. So if you have a function f of x, in this case you have a one variable function, the fundamental theorem of calculus states that when you integrate the derivative of a function with respect to x in terms of dx, then this is just equal to, by the way, your limit is from a to b. This is just equal to the function f, small f, minus f of b, which is the value of f in the final point b, minus the value of f in the initial point a. Or you can also use this in just bear in mind that the capital F of x is just equal to the derivative of f with respect to dx. So here, as the geometrical interpretation, according to equation 1.33, which we have gone through before, df is just equal to df over dx times dx, and you can just cancel that one, so that's just equal to df. So that is the infinitesimal change of in f going from x to x plus dx. So the fundamental theorem 1.4 says that if the interval is chopped from a to b, you have here the function, that is the function, and it's chopped here. So you chopped it from a to b in figure 1.25 into many tiny pieces dx, and add up the increments of df from each little piece, will result to the change of f minus f of b minus f of a. That is the final value of f minus the initial value of f in consideration. Now we'll go to the fundamental theorem of gradients. In this case, you have, in general, you have a function t of x, y, and z, and then you integrate it starting from point A to point B. And you move a small distance dl, for example here, and then you can get the increment of that. So that is just the gradient of t, that dl is just equal to the total differential of t. This is by equation 1.37 as before. And then if you move further by a small amount dl2 here, the incremental change in t will be del of t dot dl2. So by this manner of proceeding by infinitesimal steps, point B will be reached. So you can reach point B. At each step, the gradient of t is computed at that point and dotted to the displacement dl. This gives the change in t, and evidently the total change in t in going from A to B along the path is this one here. Why? Because you have, this is supposed to be just dt. So this is just the integral of dt from A to B. And so you have because this is just integral of A to B of dt. So you will have this one here. The gradients has a special property, and that if you integrate it with if you integrate the gradient that to dl from A to B, This is path independent, meaning you can use any path to reach out from the initial point to reach the final point, and you still get the same integral. Any path will do. So a straight line path can do as well. So you can use a curved path or any path, any curve. But when you also integrate it with a straight line, it's also the same. So that means that when you integrate from one point to another point and then back to the original point, you are doing the integral in circle or in a closed loop. Then the integral of a gradient dl would be equal to 0. So as an example here, you have t equals xy square. Take the point A to be the origin here, and B to be 2, 1, 0 here. The value of z is 0. This is 0, 0, 0. So that's and so that means your z, the value of your z in point A is 0, and the value of your b of the value of your z at point B is also equal to 0. This means that the 2 points lie only in the xy plane. So you can integrate using this path, going through 1 and then 2 to reach B, and then you can also go from A to B directly in one line. So let's check if the integral using this path here is just equal to the integral using this path here. So dl, as we have previously used it, dl in Cartesian plane is just this one, and your t, as you can calculate, that's t is equal to xy squared. So you will have delta, the gradient of t. The gradient of t would just be d partial of t with respect to x, x hat. You have here, wait, this is so you have here x side direction x hat plus partial of t with respect to y hat plus partial of t with respect to z hat. But there's no z component, so this is just equal to 0, and then you have partial of, you have t is equal to x y squared. So partial of t with respect to x would be equal to y squared, and that's this one. And you have x vector x, unit vector x, then partial t with respect to y is equal to 2x y, and you have the unit vector here. So for segment 1 here, the value of y is equal to 0, and for segment 2 the value of x is equal to 2. Here the value of y is equal to 0, so it does not change until, but x will have a change from 0 to 2. In segment 2 the x is constant, which has a value of 2, but the y is from 0 to 1. So y is equal to 0, and then your dl, since y is equal to 0, the derivative of y is just also equal to 0, so this is equal to 0, and then of course your z is equal to 0, so your dz is also 0, so your dl will just be this one. And when you dot dl with the gradient of t, it's just the x component, so you will only have this one here, and this is now dx. But what we can say about y is that's 0, the value of 0, so everything is 0, so this is 0, so integral of 0 is just equal to 0. So for segment 2 x will be equal to 2, but the derivative of x, which is 2, is just derivative of x, which is a constant 2, is just equal to 0. So in that case your dx here is equal to 0. That's the derivative of 2, which is a constant, but the y changes, so the y remains, and of course z is 0, so derivative of 0 is also equal to 0, so this is equal to 0. So if you dot derivative I mean gradient of t with dl is just in the direction y hat, so it will, this is the only term that survives. This one will be 0, and so you have this one here, and your integral of gradient of t dot dl would be, by the way, y has a value of 1 to 0, 0 to 1, so you will have, and in this case you also have x is equal to 2, so 2 times equals 4y dy, and so you will have the integral of y with respect to y would be y squared over 2, so 4 divided by 2 would be 2, and so you will have equal to 2 here. Look, if you evaluate that, the total line integral is 2, and this is consistent with the fundamental theorem, that one there. Now we can calculate the same integral along step 3. We can calculate along step 3 the straight line from point A to B. So in this case, if we go back to the figure, here, from point A going to point B, both x and y are not they're dependent of each other. So as x progresses, the y also increases. here. It's not constant like this, so they have a relationship. So you have here, you can get the linear relationship by equation of the line using 2 points. So you have here 0 0, and then you have 2 1. So you can use x minus 0 over y minus 0. This is just equal to 0 minus 2 over 0 minus 1. So x over y is just equal to negative 2 over negative 1 is 2. So your x is equal to 2y. And you can use that relationship to integrate through segment 3. So x is equal to 2y, or y is equal to 1/2 x. So in this case, you will have the dl. In this case, your dl will be, since they are both changing, so your dl would contain these two components. This is, of course, z is equal to 0 again, so you can just leave that. So you have now, if you dot the gradient of t with respect with the dl, then you will get this. And then by substituting this one, if you want to just integrate with respect to x, then you can substitute y square. This is just equal to 1/4 x square, and this one is just equal to you have xy, so you can have this x, so this is x square, and then you will have 1/2 in terms of, but you also have dy here, which is equal to 1/2 dx. So you will have you have another you will have another factor of 1/2 here. So everything will just be 3/4 x squared dx. And so if you integrate that, so here you now integrate that. Let's just integral. The x has limits 0 to 2, so this is just 3/4 x squared dx, and so you have 1/4 x cubed evaluated from 0 to 2, and this is just equal to 2. So any path, the path using the two segments and the path using a direct line from point A to B, the integral is constant 2, and so therefore you have a path independent integral. So this gradient here is path independent. So for the fundamental theorem of divergences, you have the integral of the divergence of a vector function v with respect to some volume, differential volume or infinitesimal volume, with respect to some volume v, is just equal to the closed integral of the vector function b dotted to differential area. This means that you have the divergence of v going out of the volume is just the integral of v over a closed surface. This theorem has three special names. You can call it Gauss law, Green's theorem, or Divergence theorem. This says that the integral of a derivative, divergence in this particular case, over a region, which is the volume, is equal to the value of the function at any boundary, the surface that bounds the volume. So you have a volume integral. You can convert it into a surface integral, where the surface must bound or must cover the volume. So you have here a volume integral, and then you have a surface integral, where the surface S bounds the volume. So if you have a sphere, you're integrating the vector, and then that's equivalent to integrating the function using the surface that covers the sphere. So here you have the geometrical interpretation. If V represents the flow of an incompressible fluid, then the flux of V, which is the right side of the equation here, the flux, is the total amount of fluid passing out through the surface per unit time. The divergence measures the spreading out of the vectors from a point, a place of high divergence, like a faucet pouring out liquid. If there are lots of fluids in the region filled with incompressible fluid, an equal amount of liquid will be forced out through the boundaries of the volume, or the boundaries of the region. So you have here a simplified illustration. The faucets within the volume, the integral of that, is just equal to the flow of the fluid through the surface. That's just the meaning of it. So we can check this by example. So in this example, check the divergence theorem using function V on the unit cube. This means the sides of the cube is equal to 1. Situated at the origin, figure 1.29. So you have a volume here, which is bounded by 6 surfaces. You have surface 1 here, and then surface 2 at the back, and you have surface 3 on this side, and surface 4 on this side, surface 5 at the top, and surface 6 at the bottom here. And so you can use this integral to solve the divergence, the integral of the divergence, or you can also use this one to see that they're equal. So here you have, if you take the divergence of V is now partial with respect to x plus partial with respect to y hat plus partial derivative with respect to z hat, and then you dot it with v. So you can take the partial derivative of this and partial derivative of this one here, and of course that one there. So here this does not have x here, so this will just be 0 plus the partial with respect to y. This one gives you 0 and this one will give you 2x plus, for this one here, the partial derivative of this one with respect to z is just 2y. So this is just equal to 2 times x plus y. So that's the divergence of v. So you will have this one here, 2 times x plus y integrated with respect to d tau, and then you have 2, take that out of the integral, so this is from 0 to 1, 0 to 1, 0 to 1, and anyway x and y are independent of each other, so you have dx plus, x plus y dx dy dz. So you can integrate this with respect to x first, and so you will have x plus y dx. It would be, when you get the value, you get the integral from 0 to 1, this would be 1/2 plus y. Since the integral of this is x squared over 2, and the integral of this would be yx, and you evaluate from 0 to 1, this will give you this one here. And then after integrating that, you can integrate with respect to y. So you have 0 to 1, 1/2 plus y dy equals 1. So the integral here is equal to 1/2 y, and then here you have y squared over 2. You evaluate from 0 to 1, and then you integrate z because it's also, well, independent. So you can integrate dz, so this is just equal to 1. So if you combine everything, you will have the divergence of v, integral of that with respect to d tau, is just equal to 2. So if you want to evaluate the surface integral, there are 6 surfaces, so you have to add the integrals of the 6 with respect to the 6 surfaces, because you are going to integrate with a closed surface. Here 1, 2, 3, 4, 5, 6 surfaces, so you have to get the integral of that. So for each one, you can evaluate this, and this. So for surface 1, this is just, for surface 1 you only have this surface here, and that is just the xy plane, and so you will have, in this case you will have I or x hat dy, I mean this is the z, sorry, this is the zy plane, so you have x hat dy dz. So you can, so you only have to integrate this one, not, you don't have a component of the y hat and the z hat in this surface, so you can only integrate this one here. So that's why you have y squared dy dz. And so if you integrate that, this is y cubed over 3, the integral of dy squared dy, evaluated from 0 to 1, that's y cubed over 3, so that's 1/3. Then you integrate dz from 0 to 1, which is equal to 1, so you have 1/3. This one, the surface 2 is on the opposite direction, so you have negative x hat, that's why there's a negative here, and so you'll be able to find out that it's negative 1/3. And then similarly you can also you can try to evaluate it yourself. So you have to explain that because you have to summarize all the examples. And so anyway, everything will boil down to this, and that's just equal to 2, as you would expect, because they're supposed to be equal. Then we now go to the fundamental theorem of curls. This theorem is also named as Stokes Theorem. Stokes Theorem. So this one here, you have a curl of a vector function, which is also a vector dotted to a surface, and this is just equal to the line integral over a closed curve or a closed path P. The divergence theorem, you have integral of v, that d tau, you have a volume, this is just equal to some surface integral that dA here, and this one, it's like a surface integral, and then you have a line integral. So the integral of a derivative, in this case you have a curl over a region, is equal to the value of the function at the boundary. And you have the dA here represents the differential area over a region, and the dL here is the differential of the path or the curve that surrounds the surface area, the area. So we can do some example. But before that, we'll go to the geometrical interpretation. Recall that the curl measures the twist of the vectors v. So you have the curl of each vector here. A region of high curl is a whirlpool. So in this case, you have small curls, and then that one will have an effect on the boundary, and the boundary also moves this this way here as an effect of the small curls. So the small curls has effect on the boundary here. So may I just read that the integral of the curl over some surface, or more precisely the flux of the curl through that surface, represents the total amount of swirl. It can be determined just as well by going around the edge and finding how much the flow is following the boundary. By the way, you have to be consistent with your right hand rule, such that whenever you have curl rotating counterclockwise, the direction of your thumb points to the differential surface area. So you have, when you use your right hand, you have to make sure that your right, it's of course always the direction of the area. Your thumb points to the direction of the surface area. But usually the area, the direction, the differential area, the direction of that will always point positive when you have a closed surface. But if you have an open surface, you have to do the right hand rule. That's the most important thing that you have to be careful with. So this one here, again, as with the fundamental theorem of divergence, for the integral of a curl over surface is dependent only on the boundary line, not on the particular surface used. So if you have a boundary line here like that, for example, this is just an example. So if you have a flat surface, the integral would be the same if you have a curved surface. It doesn't matter. So if you're doing the integral, so if you have a closed surface, that would be, the integral would be 0. So we'll now go to the example. So here, suppose v is equal to 2xz plus 3y square y hat plus 4yz square z hat. So in this case, your v has no x component. So we'll check the Stokes theorem for the square surface shown on figure 1.33. So you have a surface that is bounded by 4 segments. This is the first segment, the second segment, and the third segment, and this is the fourth segment with the respective direction here. So you have to take note of the direction. Here's going to the right, going up, going to the left, and going down. So we'll take the cross product between the del operator and V, and the cross product would be the cross product of del and V is just this one. You can perform that one using the previous lecture. You can find it there. And then of course you have dA using your right hand rule. This is a path going in this direction. I mean counterclockwise, so your dA must be pointing in the positive x direction out of the page. So that your dA is just dy dz, because this is plane zy. So dy dz x hat. So that could also be dA equals dy dz x hat, but when you do the opposite direction, that's counterclockwise, so you have to follow you have to curl your palm counterclockwise, so you have your x direction with your right hand or right thumb. So if you impose a clockwise direction, then your right thumb will do the opposite direction. So now we can do it like this. So in that plane, your curl would be this one here, but you'll be dotting it with the dA, which is in the x hat direction, so you can only have this one. And of course here you have x is equal to 0, so that this one will go to 0 and you're left with 4z here because x is equal to 0. So you're now integrating this one here, 4z squared. dy is independent of z, so you can integrate that. Dy from 0 to 1 is just equal to 1, and then you have 4z squared. You integrate that with respect to z, that's 4 z cubed over 3, and so the total integral will give you 4 thirds. So if you use this one here, use this formula here, you'll be dealing with the segments enclosing the surface. So you have here segment 1, segment 2, segment 3, and segment 4. For segment 1, you have y, of course, from 0 to 1, and then x here is equal to 0, and the z is also equal to 0. That's for segment 1. For segment 2, your z is from 0 to 1, your y is equal to 1, and your x is equal to 0 for segment 2. For segment 3, your z is equal to 1, your y is equal to it goes from 0 to 1, and then your x is equal to 0. Everything here in this plane is equal to 0. For your fourth line, you have z going from 1 to 0. I mean, in the third segment, your limit should be from, because your y goes from 1 to 0. Looking at the direction here is very important. So let's do the integral. So you have v dl, in that case for segment 1 is only dy. So you will have v dot dl. This is your let's check again. For segment 1, you only have dy, but so you only have to dot it with this component of v. So you will have, and also you have z equal to 0, as z equal to 0 and x is equal to 0. So everything boils down to this integral, and that's equal to 1. For the same argument goes for segment 2, segment 3, and segment 4. So here you can do it yourself, and you'll find out that the closed integral of v dot dl is also equal to 4/3. So you have now proven that the integral of the curl of v dot dA with respect to a surface is just equal to the integral with respect to a path of v dot dl. The path here encloses the surface. So this is all for this session. We will continue with the lecture 6 in the next class.